So to understand Ohm's law, the first thing that we need are the key components in the definition of Ohm's law. So for Ohm's law, we have three variables that are going to show up at the end. We have V, which we have already looked at in previous classes, which is just the voltage or the potential difference. And then we have I, which is just the current. And again, current, we have seen it already. But then we have the third term that we haven't seen so far, R for resistance. So let's start by describing what resistance is before we go on to define Ohm's law. So what is resistance? Well, resistance is just the ability of current. So just the ability to resist current, or the difficulty current encounters as it is moving in a conductor. So that is what resistance is. So it's just more like resisting, or the resistance. Again, I'm using that term. It's just the difficulty current encounters as it is moving in a conductor. Now, how do we account for current? Well, for resistance. Well, this resistance depends on the material that current is moving in. Let's take, for example, you have a conductor or a wire like this. You see, this wire or this conductor will have some form of thickness. So the wire will have some form of thickness, and that thickness will correspond to some cross-sectional area A. And the length of the material of the wire can be taken as L. Now, what happens? You see, depending on the material that we're dealing with, whether it's copper, it's aluminum, it's iron, and so on, it has some form of resistivity or some form of hardness to the flow of current, basically it's resistivity, some constant. This resistivity, will give it rho as the symbol, and this resistivity depends on the material that we're dealing with. So different materials will have different resistivity or resistance. So resistivity. Now with this, we can now come up with a definition of resistance in terms of the length of the material. So the resistance, should you need this formula, resistance can be calculated if you know the length of the material. So it will actually be directly proportional. So resistance will be directly proportional to the length of the wire or the conductor through which the current has to flow through, but it will be inversely proportional to the cross-sectional area of the material. So this is what resistance will be. Now, what does this imply? It implies that if the wire is longer, then you expect that there will be more resistance. If the wire is shorter, if current is moving through a shorter material, then the resistance will be less. So you lose more energy, and there'll be more resistance as current is moving through a longer wire. But look at this, there's area as well. Area also affects what the resistance is going to be. So what does this imply? It implies that if you have a thin wire, very thin, a thin wire will attract more resistance. So if the cross-sectional area is way too small, very small, like this one, for example, here we see that the cross-sectional area is very small compared to the one on top. So if the cross-sectional area is small, then the resistance will be greater. But if the cross-sectional area is bigger, then the resistance will be less. So this is what we're seeing. And when the proportionality symbol changes to equal sign, we end up with, we introduce a constant, and in this case, this will be particular to the material, which is the resistivity. So we end up with this as the formula for resistance when current is passing through a wire or a conductor of length L and cross-sectional area A with resistivity rho. So this is what we have there. Now, with this in mind, we can then move on to look at what Ohm's law itself is. Now, what is Ohm's law? So, of course, before I state Ohm's law, I should state that here resistance has units of ohms. So, resistor has units of ohms, or symbol omega, like that. So, let's now move on to define Ohm's law, since we have accounted for everything that is necessary there. Now, what does Ohm's law state? Ohm's law just tries to account for the relationship between the current passing in a material to the potential difference that is driving that current through the material. It states that the voltage across a resistor will be directly proportional to the current flowing through the resistor. So if you have a resistor like this, now what Ohm's law states here is that the current, or let me say, the voltage across this resistor. So if we have a plus here and a minus, so the voltage across this resistor will actually be proportional to the current flowing through that resistor. So if the current flowing through it, you can say the current is in this direction, and let's label it as I. So the voltage across the resistor will be proportional to the current I. And when the proportionality changes to an equal sign, what happens? We introduce a constant. And in this case, the constant will be the resistance of that particular resistor. So this becomes I multiplying the resistance. So this becomes the formula that arises from Ohm's law. So when defining Ohm's law, we just talk about the voltage across a resistor being proportional to the current passing through that resistor. And the resistance only shows up when the proportionality changes to an equal sign. So this is what Ohm's law states. Okay, any questions there? Now, you should see that from this equation, we can easily make resistance subject of the formula, and we end up with R being equal to the voltage divided by the current. Here, of course, we see the voltage will come with the unit of the volts, while the current will come with the units of the amps or the ampere. Now, a combination of these two, we see since these are giving us resistance, so it means that the volt per amp has to correspond with the ohm. So this has to be proportional to the ohm. So we can now conclude that 1 ohm is actually equal to 1 volt per ampere. So those two, or those, have to relate in that way. Okay, so basically that is what Ohm's law gives us. Thank you. Okay, having looked at resistance and Ohm's law, we now introduce a component or a quantity that is just as useful as resistance, but we will rarely look at this. Just something you have to keep in mind. Sometimes it will be examined as well, and that is going to be conductance. By symbol, conductance, we use capital G. Now, what is conductance? So it will be basically just the reciprocal of the resistance. By reciprocal, I mean the inverse. So conductance is just 1 over the resistance. So if you have the resistance, divide it into 1, and what you will get will be the conductance. Remember, we had, from Ohm's law, we had voltage being equal to IR. And from this, we ended up with R being equal to voltage over I. If we try to now express conductance in terms of this, we're going to have, since conductance is 1 over R, so now where there's R, we can end up with 1 over V over I. So this is 1 divided by V over I, or conductance will now take V over I. It's not necessary for you to memorize this, as long as you recall that conductance is 1 over resistance, then you're going to be okay. Now, apart from the formula for conductance, the next thing that you need to know about conductance are the units. The easiest one for you to know in terms of the units for conductance, since remember, conductance is the inverse of resistance, even the units are actually related. We know to say resistance has units, the ohm. Well, conductance has a similar unit. Basically, it's the same ohm, but inverted. So we can look at it as this. Now, in terms of naming, remember, resistance has the ohm like this. Conductance will have the ohm backwards. So it should be M first, H, then O. So this will be to mean this. So that is the unit for conductance. Another unit for conductance that you will find commonly being used is going to be the Siemens. So another unit that can be used for conductance is this. In symbol, usually this will be denoted by capital S. So this will also be used to mean conductance. So we have seen 2 units for conductance. You have 1 Siemens being equal to 1, the ohm, but written inverted like that. But you also saw to say conductance can be seen as what? We had, sorry. I wrote V over I here. When this is simplified, this becomes 1 multiplying I over V. So this is not V over I. It is instead I over V. Notice that resistance was the one which is V over I. Conductance will be I over V. So from here, I over V, I will have the amp, V will have the volt. So that we end up with amp per volt, 1 amp per volt. Okay, but here's just one thing that, so we've seen that conductance is the reciprocal of resistance. But as you can tell from the term conductance, it is just, you see, resistance was the to resist flow of current. Conductance is the ability of an element to actually allow current to pass through it. So it is an ability of an element to conduct electric current. So I hope you're getting that. Resistance was the difficulty, while conductance is how easy it is for current to pass through an element. So that is the difference between conductance and resistance. Let's look at a few examples. So consider this basic example where we have an electric iron that draws 2 amps at this voltage. Find its resistance. So again, by Ohm's law, we have I. So resistance will just be V over I. Again, this is straightforward. The voltage is 120. And the current here is 2 amps. So you see the resistance comes here as 60 ohms. So this was straightforward. Let's find another one. Okay, so in this example, we want to calculate the current I, the conductance G, and the power P. And then we have this basic circuit. And let's see what we have to do here. So let's see. The first thing is the current I. Because here you only have one resistor, don't have to stress about finding the total resistance because you only have one. So by Ohm's law, current can be seen as voltage divided by the total resistance R. The voltage is 30. Total resistance, this is in kilo ohms, so you have to write it in ohms. So you know to say 5 kilo ohms is equivalent to 5,000 ohms. So from there, this is divided by 5,000. So when you do the math, this comes out as 6 milliamps, or the two come out as 6 by 10 to the power minus 3 amps, but this is what can be taken as 6 milliamps. So after you get the current, you can now move on to look at the conductance. So what is conductance? Conductance, remember, is 1 over R. So in this case, what is our R? Our R is this, 5 kilo ohms. So because of that, we can now just say this is 1 over, but we can't say 5, just 5 kilo there. We have to convert it to ohms. This will be 5,000 ohms. So when you do the division, this will come out as 0.2 by 10 to the power minus 3 Siemens, or you can write it as 0.2 millisiemens. That becomes the conductance. And the last part is the power. In electric circuits, we know to say power is voltage times current. We already have the voltage supplied, that is 30 volts. And then we have the current. The current here, we did find the current as 6 by 10 to the minus 3. So when we multiply this, we get 60. So that's 60. 6 by 3, that is 180. And then this is by 10 to the minus 3. This is power, so we have the watts. So this is what comes back to 180 milliwatts. So this becomes the power there.